3 doors. Behind one of them, a car. Behind the other two, goats. You pick door 1, the host, who knows where the car is, opens door 3, a goat. And now he asks you, do you want to switch to door 2? Almost everyone answers the same way. It doesn't matter. 2 doors left, 50-50. Here's my bet against all of them. Switching doubles your chance of winning. Sounds impossible, doesn't it? Then you're in excellent company. Nearly 1,000 people with doctorates, statisticians, mathematicians, professors, put exactly that objection in writing, and every single one of them was wrong. This is the story of the most famous argument in modern mathematics. It pitted one woman against an entire country, embarrassed universities, and took down one of the greatest mathematicians of the century along the way. We'll get to him. And it doesn't start in a lecture hall or in a research journal. It starts in a Sunday magazine column. At the end of it sits a lesson bigger than any game show, a lesson about certainty and about when to distrust it. But first things first, it all begins in 1990 with a reader's letter. September 1990, Marilyn vs. Savant writes the column Ask Marilyn. She was listed in the Guinness Book of Records for the highest IQ ever measured. A reader named Craig Whitaker sends in exactly our 3-door question. Her answer is 2 sentences long. Yes, you should switch. The first door has a 1/3 chance of winning, but the second door has a 2/3 chance. She will end up defending those 2 sentences across 4 columns. The game, by the way, is named after a real TV host, Monty Hall, of Let's Make a Deal. Did he ever actually play it like this on his show? Hold that question, because first America loses its mind. Roughly 10,000 letters pour into the magazine, nearly 1,000 of them from PhDs. A statistician from Florida writes, "You blew it, and you blew it big. Shame." A Georgetown professor sees the nation's math education in crisis and demands, "How many irate mathematicians are needed to get you to change your mind?" Others get personal. 2 readers explain, in all seriousness, that women simply look at math problems differently than men. Keep this in mind while they rage. She is the only one in that pile of letters who is right. The fight simmers for months across newspapers and lecture halls. On one side, America's assembled expertise, titles, tenure, authority. On the other, one columnist with 2 sentences. And here's the beautiful part. We don't have to believe anyone. No authority, no title, not even her. This question is one of those rare disputes you can settle entirely on your own, with nothing but 3 cases and 2 quiet minutes. So let's settle it. You always pick door 1. The car is equally likely to be behind door 1, 2, or 3 cases, and there is nothing else in the world. Let's walk through them, one by one. Case 1. The car is behind door 1. The host opens one of the goat doors. You switch and lose. Case 2. The car is behind door 2. Now the host has no choice. He must open door 3. You switch to door 2. You win. Case 3. The car is behind door 3. Again, no choice. He must open door 2. You switch. You win again. 3 equally likely cases. Switching wins in 2 of them and loses in 1. 2/3. That's the whole proof. No trick, no advanced math. It fits on the back of a napkin. And still, I know exactly what your gut is saying right now. There are 2 doors left. One of them has the car. 50-50. That feeling is astonishingly strong. It survives tables, it survives proofs. It made professional statisticians write furious letters to a woman who was simply right. The George Mason professor who wrote, "You blew it?" He took a while and then wrote in again, "After removing my foot from my mouth, I'm now eating humble pie." Credit where it's due. But why does intuition lie so stubbornly here? That's the genuinely interesting question. The mistake lives in a single reflex, 2 options, so they must be equally likely. It's a comfortable reflex, and sometimes it's even correct. For a fair coin, it's exactly right. But probability doesn't count doors, it counts the paths that lead to them. A lottery ticket also either wins or loses, and yet the lottery is not a coin flip. Your first pick was a shot in the dark, 1/3, and it was never more than that. That number freezes, no matter what happens afterwards. The remaining 2/3 sat on the other 2 doors from the very start, and that is exactly where they stay. And now, the most underrated character in this whole story, the host. He doesn't open just any door. He knows the car, and he filters for you. From the 2/3 side, he is guaranteed to clear away a dud, every single time. What's left is not a random door. It is 2/3 of probability, concentrated into one single door. Switching doesn't mean guessing again. Switching means pocketing the host's knowledge, knowledge he just handed you free of charge. If your gut is still on strike, good. Because now it gets 2 arguments it simply cannot argue with. Argument 1. We make the game bigger. 100 doors, 1 car. You picked door 1, a 1% chance, let's be honest. The host, who knows the car, now opens 98 goat doors, one after another, all the way down the wall. What remains? Your door 1 and, say, door 67. Still 50-50? Your 1 in 100 guess. Against the one door he left standing out of 99? Why that one, of all doors? Suddenly everything in you screams, switch! With 100 doors, switching wins 99 times out of 100. And with 3 doors, it is the same principle, just quieter, 2 out of 3. Argument 2, try it, not 10 times, 1,000,000 times. I simulated the game 1,000,000 times, one half stays stubborn, the other half always switches. The result, staying wins 33.4%, switching 66.6, exactly the 2/3 from our table. And this is precisely what Vaux Savant asked schools to do back then, play it with cups and coins. More than 1,000 classroom experiments confirmed her, and about half of her printed critics publicly changed their minds. You can rerun it yourself, by the way. 30 rounds are enough. The switchers land around 20 wins, the stayers around 10. It's hard to shout down data, but one doubter is still missing from this story, the most prominent one of all. Paul Erdős. Around 1,500 mathematical papers, the most prolific mathematician of the 20th century, a man who understood probability better than entire faculties. When a fellow mathematician showed him the door problem, he said, "No, that is impossible. It should make no difference." His friend tried decision trees. He tried Bayes' theorem. Erdős waved it all away. Only when a computer played the game 100,000 times and the 2/3 line appeared on the screen did he give in, grudgingly. If even Erdős stumbles here, your stubborn gut is nothing to be ashamed of. Pigeons. Seriously, in 2010, 2 researchers had 6 pigeons play a peck version of the game, food instead of a car, lit keys instead of doors. On day 1, the birds switched 36% of the time. After 30 days, 96%, practically optimal. Students got the same task for 200 rounds and plateaued at about 66%. The pigeons beat us because they simply keep count of what produces food. We, on the other hand, ponder and theorize and think ourselves right into the trap. Which brings us back to a condition I've been using silently this whole time to confess. Everything we proved hangs on a single word. The host knows where the car is and opens a goat door on purpose. Now try the variant by mathematician Jeffrey Rosenthal. The host slips on a banana peel and, falling, knocks open a door at random. By pure chance, it shows a goat. Same picture, same 2 doors, and suddenly 50-50 is correct. Switching gains you exactly nothing. Why? A random host doesn't filter. He could just as easily have exposed the car. The fact that he didn't was, this time, pure luck, and luck carries no information. The paradox doesn't live in the doors, it lives in the knowledge behind them. Which leaves our question from the very beginning, did Monty Hall himself ever play it this way? In 1991, he ran the game with a journalist at his own dining table, switching won 8 out of 10 rounds. The math? He confirmed it on the spot. But about his real show, he said, "Where does it say I have to let you switch every time? I'm the master of the show." He offered cash against the door, red faces, played on nerves. His only advice, if you can get me to offer you $5,000 not to open the door, take the money and go home. The math holds, but only as long as the rules you're computing with actually hold. So who actually got it wrong? The 1,000 doctorates? Their intuition? Maybe the most honest answer is this. Their gut answered the wrong question. It computed the slipping host, but the question was about the knowing one. 50-50 was a perfectly correct answer, just to a different game. And that is the real prize behind door 2. Precise questions beat loud certainty every time. So the next time everyone declares you crazy, colleagues, comment sections, experts, maybe you just looked more carefully than 1,000 professors. If stories like this one grab you, there are more where it came from.